You're muted. We can't hear you. We can't hear. We can't hear.
Huh. Yeah.
Is it okay?
Yeah. Can you redo the introduction, please? Yes.
Can you redo the introduction?
Yeah, you turn on the slide here. So accidentally we were muted. So for the benefit of online audience, I wish to say again that today's speaker is Professor Pranab Sen. Currently, he is Dean in the School of Technology and Computer Sciences at TIFR. And before becoming a faculty member at TIFR, he in past studied in this very college. After this college, he went to IIT Bombay for his BTech, and he was then came to TIFR for a PhD. And a chance introduction with Professor Love Grover prompted him to switch to area of quantum computation. And today he's going to tell us about recent breakthrough prizes that was awarded to the area of quantum, broadly speaking, quantum.
Okay. Thanks, Ulhas, for the introduction. I hope I'm audible to the online audience also now. Yeah. Okay. Yeah. So let me turn on the slides. Yeah. It's both fun and an honor to talk at Chai and Y, and yeah, I'm very pleased to be speaking at this August College, Rupal College. So I passed out from here in 1990, so it's 32 years back, and it just feels like yesterday. I mean, I've been walking on the campus a little bit and taking some photos. Even louder. Okay. I hope it doesn't overshoot the online. Yeah. Okay. Okay, I'll speak louder. Yeah. So it's a great pleasure to be here at Rupal College. I passed out from here in 1990. I did my 11th and 12th standard out here, and so 32 years back. But it just feels like yesterday. I mean, it's a little spruced up, and there's a big high-rise building outside, which was not the case at that time. But it's still recognizable in parts. Okay. Yeah. Okay. So today I'm here to talk about the 2023 Breakthrough Prize in Fundamental Physics. So if you do not know, the Breakthrough Prize is a relatively recent prize. It's about 10 or 12 years old, started by a Russian origin guy. I mean, he's a tech billionaire. And the aim was to create a set of prizes competing the Nobel Prize. Okay, so the prize money is about 3 times the Nobel Prize. It's quite prestigious already. And now that I'm here, so shortly after the 2000. Yeah. Yeah. Okay. Yeah, now that I'm here, so I was asked to speak about the 2023 Breakthrough Prize, which was announced less than a month ago. But since then, the 2023 Nobel Prize in Physics has also been announced, and these are the 3 persons, the 3 gentlemen here, Aspect, Claus, and Zeilinger. And it so happens, coincidentally or otherwise, their work is related to their work. Okay, so all 7 of them have different works. Okay, but there is a common theme of quantum information science running behind. So as a hat tip to the 2020 Nobel Prize in Physics, I'll talk a little bit about that also, how their work relates to the works of these people. But yes, it's mostly about these persons. And some of you may have seen the publicity video put up by breakthroughprize.org, okay, advertising the 2023 prize. So these stills, in fact, these pictures are also screenshots from that video. So we'll play that video again, and we'll comment on it as we go. Okay, But before we get into Breakthrough Prize and Nobel Prize and all that, so let's do something which, again, I think many of you already know. So we will talk about cryptography, the art of secure writing. So we'll talk of the oldest and the securest crypto system, very old. It's called the one-time pad. Okay. And this is a schematic diagram. So there is a sender who is traditionally called Alice. There's a receiver of messages who is traditionally called Bob. Alice has a message to send. So this is the plain message, called the plain text. But this has to be protected from adversaries. So there is an encryption procedure which goes on. And to do the encryption, we need a key which is called the one-time pad. Okay. So some operation is done on the plain text using the one-time pad. And this is the encoded text called the cipher text, which presumably nobody else can read. And Bob, who is at the receiving end, also has the copy of the same key, the same one-time pad. Using the one-time pad, the Bob can decode from the cipher text and recover the original message, the original plain text. Okay. And some adversary who is out there who doesn't know this one-time pad, this so-called secret key, that adversary has no idea of looking at the cipher text, what the plain text is. So here is an example how it may work. So let us say I take the English alphabet, and for convenience, I number the alphabet using numbers from 0 to 25 in the natural order. Okay. And let us say my input is the plain text message vault tree. Okay. And the one-time pad or the secret key is this gibberish looking thing. Okay. This is some random looking gibberish. So note that the length of this secret key, the keyword, should be the same as the length of the plain text in the one-time pad. So same number of letters. And now the output is the cipher text, which again looks like gibberish. But nevertheless, Bob, who has the keyword, can decode from the cipher text back to the plain text and recover the vault. So this is how it works. So the part one, which is the encryption, plain text to cipher text. So take the plain text vault tree, convert it into a sequence of numbers like this. Okay. Take the key, think of it as the corresponding sequence of numbers, and just add the numbers. Okay. So 21 plus 0 is 21, 0 plus 23 is 23, 20 plus 3 is 23. So I'm just adding the numbers location wise, location by location. Okay, I get these numbers, convert them into alphabet. This is the cipher text. And to decrypt from the cipher text back to the plain text message, so take the cipher text, okay, then convert it back into numbers, and then just subtract this key out from there. Okay, so from 20, let us say, let's take the fourth guy, 18. Okay, so 18 is the fourth alphabet in the cipher text. Look at the fourth key, that is 7. So 18 minus 7 is 11. Okay, and so the plain text is 11 out here, which is the letter L. Okay, so this is how from the cipher text I can subtract out the key and recover the plain text. So very simple thing. An adversary who doesn't know this key has no idea by looking at the cipher text what the message is. It's called a one-time pad because the key can be used only once, and we'll appreciate why that is the case soon. So this is the highest grade of security. So the most important and secret wartime communications are done with the one-time pad. So earlier they used to have books, actually real books, paper books of one-time pads. Now, of course, things are done with wireless and computers. Okay. So how is it used? So the one-time pad is truly the only unbreakable encryption method, but its use is impractical for many modern applications. Okay, only the most extreme applications use it these days, because our crypto system, this entire system, must meet the following conditions. First of all, the key size must be the same as the length of the plain text, the message being sent. Okay, so if you are sending a message of let's say 1 megabyte, you need 1 megabyte of key. Okay, so that's a serious problem. The key must be truly random. Okay, I mean, it should look like gibberish. So how do you generate 1 million random numbers? The key can never be reused. That's the name one time, and we'll see the problem with that. The keys cannot be reused. So I send a 1 megabyte file, encrypted with a 1 megabyte long key. 5 seconds later, I have to send another 1 megabyte file. I need a fresh key, which again has to be 1 megabyte long. It has to be truly random, independent of the previous key, so on and so on. And this is the severest constraint. The keys must be securely shared between the sending and receiving parties in advance before all the communication starts. So that's the in advance part. The keys must be securely shared. So securely shared means when Alice and Bob are exchanging the keys, when they're sharing the code book, okay, there cannot be an eavesdropper who is around. So if they're whispering in each other's ear, remember the walls have ears. Maybe the eavesdropper is trying to listen in. So maybe they go to the lift and share. But these days there are cameras in lifts. Okay, lift ke diwar ke kaan nahi hote. We all know that, but there are cameras now in lifts. So securely sharing between the sending and receiving parties in advance is a serious constraint. So it requires them to have met in a secure location and so on and so forth. But what if is the wartime and Alice and Bob are in two different theaters of war? Okay, there's no scope of the meeting. So this is a serious constraint. So this is the most serious constraint in practice. Okay, and this is where the works of Bennett and Brassard, the first two breakthrough laureates, come in. So to appreciate I mean, these constraints of a one-time pad, I'll have an example of visual one-time pad. So the one-time pad need not be just for sending messages which look like English text. It can be pictures also. Okay, and remember, pictures these days are encoded using bits. So I have a visual example of a one-time pad. For this, acknowledged Douglas Tavila, who is the professor at University of Waterloo. He actually works in the Institute of Quantum Computing there. Okay. So I hope you can see. So this is the encryption key, which looks like some gibberish picture. This is the ciphertext. Okay, and in fact, let me show. There are two ciphertexts. Okay. Now, so it happens that there were two messages, but both of them happen to be encoded by the same key out here. And we'll see the problem soon. But let's first try to decrypt them. It looks like gibberish because the key is really random. So what I'll do is that I'll move it around and try to place it on this. I hope I get it right. Okay. So you can see if the bit positions are aligned. Okay, the first bit, second bit, third bit are aligned. The decryption has occurred, and you can see the plain text image. Smiley face. Let us see what is the plain text image Douglas has encoded for us here. Just same. Yeah. Yeah. There we are. It is Institute of Quantum Computing at University of Waterloo, their logo IQC. Okay. So both these plain text messages have been encoded by the same key. Okay. Now let's see the drawback. So of course, it looks pretty clear that an adversary who doesn't know the key cannot figure out what any of the ciphertext mean. But let us say the adversary doesn't know the key, but he happens to get both the ciphertext. Okay. Remember, he doesn't know the key, but he has got both the ciphertext, and Alice was fool enough to use the same key to encode the cipher. So let's see what can happen. So let me put the ciphertext on each other. So the adversary can play the two ciphertexts against each other. Yeah, something flashed. Yeah. So you can see the adversary has played the two ciphertexts against each other somehow, very cleverly. And you can, some information has come out. Maybe it's not the full plain text, but parts can be figured out. You can read the I here, you can read the C here, you can read the Q there, okay. Parts of the smiley face. So this is the problem if the one-time pad is used. Okay. Now, thank you, Douglas. Now let's go back to the presentation. Okay. So this was okay, so this was an example of a one-time pad. So far it's all classical computers. The usual computers that we use we'll call classical for this stuff. Okay. Now here is where the work of Bennett and Brassard, the first two breakthrough laureates, come in. Okay. So they came up with a algorithm, or what you call a protocol, which is called quantum secret key distribution, QKD for short, using photons. Okay. And just zoom out. Yeah. So actually, the story goes that Bennett and Brassard met somewhere in a conference at the swimming pool, and then they got talking. So Bennett is a physicist, Brassard is a computer scientist like me. I mean, that's why I'm here. So half the laureates here are computer scientists, the others are half are physicists actually. So Bennett is a physicist working at IBM Research, New York. Brassard is a computer scientist working at University of Montreal, Canada. Okay. So they met somewhere, got talking. The Bennett talked physics, Brassard talked computer science or cryptography, and then they got an idea. It was published at a IEEE conference in Bangalore in 1984. Okay, so there's Indian connection already to this, and okay, and so they came up with what is called BB84, Bennett Brassard 84, 1984 cryptographic protocol for quantum key distribution. So what did they achieve? They came up with a protocol where Alice and Bob can securely exchange the secret key, long secret key, without ever having met physically. Okay, and even if there's an eavesdropper who is trying to listen in and figure out what the secret key may be, the eavesdropper will be foiled using the special quantum properties of photons. Yeah, question? Okay, so the algorithm or the protocol, okay, the algorithm which is used for encrypting and decrypting is public. Okay, so the adversary knows what strategy I'm using. The only thing the adversary doesn't know, the only piece of information the adversary doesn't know is the secret key. So in the world of cryptography, algorithms are public, keys are not. Okay, and why is this public? Because in the past, people tried to use algorithms which are not well known and all, but it so turned out that the adversary paid a bribe or something like that, got to know of the algorithm, and nobody was wiser. So it's considered much safer that you publish your algorithms, invite the whole world to come and break it, but just keep the key secret. Okay, so that actually leads to much more security in practice. Okay, further questions? So let's go. Yeah. Okay. Okay. Sorry. So the question was that was in the previous thing. So when I played off the two ciphertexts against each other, okay, how did the adversary know how to play off the two ciphertexts against each other? So that was the question. The answer was that the encryption and decryption algorithms are public. They're published in the literature. So the adversary knows what encrypting and decrypting strategies are being used. The only piece of information the adversary doesn't have is the secret key. Okay, so the adversary can play the ciphertext off against each other, and we saw what happened. Okay, so now let's pause and see the 1-minute publicity video put out by the breakthroughprize.org about the 2003 award. You have to turn off the. You have to turn off the Bluetooth.
Yeah, it is coming.
It's coming there. This will be loud.
We live in a world of information, but physics tells us that deep down, the world is quantum mechanical. This year, the Breakthrough Prize recognizes 4 pioneers of quantum information. Charles Bennett and Gilles Brassard initiated quantum cryptography and played a central role in the discovery of quantum teleportation. David Deutsch defined the quantum Turing.
Let me just fill in.
We live in a world of information, but physics tells us that deep down, the world is quantum mechanical. This year, the Breakthrough Prize recognizes 4 pioneers of quantum information. Charles Bennett and Gilles Brassard initiated quantum cryptography and played a central role in the discovery of quantum teleportation. David Deutsch defined the quantum Turing machine and laid the foundations of quantum computation. And Peter Shor invented an algorithm that could factor large numbers exponentially faster than any non-quantum rival. With these and other advances, they paved the way for quantum computers and provided clues to questions at the frontiers of physics. For foundational work in the field of quantum information, they win the Breakthrough Prize in Fundamental Physics.
Okay, I hope, yeah. Yeah, so I hope at least you could get some snippets of that video. The video is there on YouTube. I think it's there in the publicity menu. If you just search for Breakthrough Prize 2023, then you'll see it. Okay, yeah. Okay, so the video was very flashy. It said some big terms, showed some fancy images, but it's not very clear what those images are. Okay, so hopefully by the end of this talk, you will understand what those images are, and they're not random images, they're actually very interesting things. Okay, and so maybe at the end of this talk, you will appreciate what those images are, where and why they amount to a break. Yeah. Okay. Huh. Can you just move it in one corner? Okay. Okay. Yeah, thanks. Okay, so now back to the talk. So let's understand what Bennett and Brassard did. So actually, I don't have photographs from their 1984 conference talk, unfortunately, but I do have photographs from their 2002 conference talk, which took place at TIFR Mumbai. So thanks to my colleague and advisor Jay Kumar for sharing that. Okay, so yeah, I mean that itself is 20 years ago. Okay, so the aim is to distribute the secret key securely in advance without requiring Alice and Bob to meet physically. And this is impossible with the standard so-called classical computers because the eavesdropper Eve is always listening. That's the model. But it's possible if Alice and Bob use quantum properties of photons. So the quantum property that we are going to use is what is called the polarization of the photon. So that will be used to exchange the secret key. Now, why does this work in brief? If Eve has to get any information with secret key, Eve has to do what is called a quantum measurement. Okay. Now, some of you studied quantum mechanics or are studying quantum mechanics. So you know that if a quantum measurement is done, that will disturb the quantum state. In this case, it will disturb the polarization of the photon, which can be detected by Alice and Bob. So Alice and Bob will know if there's a malicious Eve around, which who is trying to eavesdrop. So that will show up as a disturbance in the polarization. So they can detect the malicious Eve. At the very least, if they detect malicious activity, they'll just abort the protocol. And if they see that the polarization states are not disturbed, they will know that nothing malicious is going on. And as you see, a secret key will come out. Okay. So this was their way out. So a little bit of background in physics. So what is polarization? So we know that light is an electromagnetic wave. So there is an electric field and there's a magnetic field, okay, traveling through space. So the electric field is oscillating. So if I look at the value of the electric field at a particular point in space, the direction is going up, up, up. Okay, the strength of electric field is increasing in the vertical direction. Then after some time, the electric will come down, then it will increase in the opposite direction. So this is what we mean by oscillating. Okay, and if I take the snapshot of the electric field at a particular point of time, so here the electric field vector is pointed upwards, here the electric field vector is pointed downwards, and so on. So I get this kind of wave pattern. Okay, so this is the wave shape of the electric field vector. Okay, so I know light is an electromagnetic wave. The plane of oscillation of electric field, in this case, is the vertical plane. So this plane of oscillation of electric field is called the plane of polarization of light. Now let us say the light is coming from a bulb, and the plane of polarization could be anything. So there are some waves which are polarized in the vertical direction. There are some waves that are polarized in the horizontal direction. Maybe there are some waves which are polarized in some diagonal direction. Okay. Now if I put a Polaroid filter, so the Polaroid filter consists of some organic molecules. So they are long molecules and they are all aligned along some axis. So think of it as between the long molecules, there are gaps. So these are like slits and the wave can pass through the slits. So this is the schematic diagram, the cartoon. So only if the plane of polarization fits into this slit, this vertical slit, will it go through. So you can see that the vertically polarized light wave passes through the filter. The horizontally polarized light wave gets blocked. In fact, it gets deflected back, as it turns out. Okay. Now, here is a paradox, which tells us that, okay, this picture is good, okay, but it's not the complete picture. And that's where the quantum property of light, the fact that polarization is a quantum property comes in. So the paradox is, though the incident light on the filter has waves with many planes of polarization, I said horizontal, vertical, diagonal, all kinds of things. It turns out that the intensity of light that is passing through the filter here is half the original. So normally you would think that the light has the waves which are polarized in all possible planes. A very small fraction of the light energy will be polarized in the vertical plane. So the intensity of light that goes through should be very low, but it's half. Why is that? Okay. So that's a mystery. And I mean, you can check, okay, only the vertical light goes through because I'll put another Polaroid filter. If it's aligned in the same way, that's called what I'm calling the analyzer. So I can see that the entire intensity of the wave here passes through here. Okay, so definitely the light which is here is only vertically polarized and all of it passes through. And further check is if I turn the analyzer by 90 degrees, okay, so that it's now analyzing the horizontal direction, this vertically polarized light gets completely blocked out here. Okay, so indeed this is vertically polarized light, and all of it passes through here, nothing passes here, and it's fine. But the mystery is, why is the intensity here, okay, half the intensity out here? So let's study this in some more detail. Okay, so in fact, you can go further and come up with what is called the three polarizer paradox. So let us say this is the original light source which is coming from the bulb. So this is the unpolarized light. Unpolarized light means the plane of polarization is there in all directions. So there is some light waves polarized vertically, some light waves polarized horizontally, some light waves polarized in this diagonal plane, some light waves polarized in the other diagonal plane, so on and so forth. So there are actually an infinity of planes of polarization. So the intensity is I0, let us say, okay, the initial intensity. I pass it through a Polaroid filter, which is vertically aligned. It turns out half the intensity is detected here. Okay. Now I put in another Polaroid filter, but this I align at 45 degrees, the diagonal thing. So you think that maybe, I know for sure this is only vertically polarized. Remember the previous diagram, this is all vertically polarized. So you may think that nothing much should go through, but it turns out half of this intensity, 1/4 of this goes through. Okay. And then I put the horizontally polarized filter out here. It turns out half of this goes through, which is 1/8. But note what I've done. I started from the vertical Polaroid filter, come to the horizontal Polaroid filter, but in the middle there was a diagonal Polaroid filter. And at the end, 1/8 of the frequency, 1/8 of the intensity is here. Whereas if you see the earlier experiment, there was vertical and horizontal, no intervening filter, only the 0% of the intensity is out here. So normally you think that the more filters you put, less intensity should go through, but something strange has happened. I put in another filter out here, then actually more intensity has gone through. So this non-intuitive behavior is what we call non-classical. It is against our everyday intuition or a classical intuition. And to analyze this, we have to use basically quantum theory, the quantum mechanical view of light. Okay. Okay. So what we see out here in the Polaroid filter is with the diagonal plane of polarization, that's 50% of light through it. And this non-intuitive behavior, the so-called paradoxical behavior, requires non-classical or quantum thinking. And then a lot of insight, lot of experiments, lot of understanding has gone. And now the modern explanation is that sure, light has the behavior of electromagnetic wave, but it also has a particle-like behavior at the same time. So in that viewpoint, light consists of particles called photons. Each photon has a quantum property called polarization. So the classical way of viewing polarization was the plane of oscillation of the electric field. Okay, but an individual particle like photon also has its own polarization. So now polarization, the same classical property has a quantum facet to it. The filter, whichever filter performs what is called a measurement of the polarization. So this is a quantum measurement of this polarization, which is now a quantum property. This measurement disturbs the original quantum state of polarization, which could be in any plane. And the outcome of the measurement is only one of two possibilities. So if I'm measuring by filter in the vertical direction, the outcome of the measurement is only two possibilities. So either vertically polarized light goes through, or the horizontally polarized light gets reflected. You don't see it here, the horizontally polarized light gets reflected. So remember, the light which is going from right to left, which is originally coming in, has polarization in all directions. This also you can check by putting in filters there and check out that it's polarized in all directions. But remember, the light consists of photons. Each photon has its own polarization. Now, there are some photons which are vertically polarized, some which are horizontally polarized, some more diagonally polarized, so on and so forth. Lots of photons, lots of polarization. But the moment I put a filter here, this amounts to a quantum measurement. Result of the measurement is some photons go through, but all of them become vertically polarized. That is the disturbance. The remaining photons get reflected. All of them are horizontally polarized. That's also the disturbance. After this measurement, you will not see a diagonally polarized photon out here. Okay. So measurement has disturbed the quantum state. Outcome of the measurement is only one of two possibilities. Okay. The filter plane, vertical, or the perpendicular plane, which is horizontal. Now, with that viewpoint, let us analyze this. So the initial light has photons which are polarized in all directions. Now I do a measurement. So the light that goes through is vertically polarized. So what about a photon which is diagonally polarized? So with 50% probability, it will go through and become vertically polarized. With 50% probability, it will get reflected back and then become horizontally polarized. So even though there are many photons, 50% of them are going through and they're all vertically polarized. Now remember, these are all vertically polarized photons. 50% of them are going through the diagonal polarization. The remaining 50% are getting reflected out here. These 50% which are going through are polarized in this direction, this diagonal direction. The 50% which are not going through, which are getting reflected, are polarized actually in this direction. That's what this diagram means. So from I upon 2, it becomes I upon 4, 50% of the goes through. Then again, remember, all the photons are polarized in this diagonal direction. I'm doing a measurement, horizontal measurement. 50% of the photons go through. All the photons that go through are now horizontally polarized. 50% of these guys get reflected. Everything which gets reflected here are vertically polarized. So 50% of 25% is 1/8. Okay, so 1/8 of these photons have gone through, and that's the explanation, the quantum. Questions? Okay, so each measurement is disturbing the quantum state. After the measurement, there are only two possibilities. Okay. Okay, so this was, of course, well known from the time of Einstein when he talked of photons and all, I mean, more than 100 years already. So in 1984, BB knew this very well. Okay, so this was the strategy. Okay, this is now the quantum key distribution protocol. So remember, Alice wants to send the message, so she has to encrypt the plain text. I mean, she has to send the key, and Bob has to receive it securely. And there is this malicious Eve who is trying to do some malicious things on the way. Okay. So what Alice does is that she first prepares a random sequence of bits. Okay, bit is a number, binary digit, 0 or 1. She prepares a random sequence of bits, but she doesn't send them directly through the classical channel or the phone line. She will encode them into photons. How she encodes into photons? She also prepares what is called the preparation basis. So you can see the polarization. What is the preparation basis? Is the choice of the filter set you use. So Alice will either use the vertical come horizontal filter set, which I'll call the plus basis. So either horizontal filter or either the vertical filter or the horizontal filter. So that's called the plus basis. So this filter set, the lower filter set of horizontal vertical, I'll call the plus preparation basis. Alice sometimes may also use the diagonal filter. So she might use the right diagonal or the left diagonal filters to prepare her photons. So this I'll call the cross basis out here, right diagonal or the left diagonal filter. Okay. So other cannot see. She cannot. The Eve is not allowed to look inside her private chip. So Alice prepares this random bit sequence. She also makes a choice of preparation basis. Okay. Then she will encode bit 1 in this basis. So bit 1 in the plus basis will be the vertically polarized photon. So we can see this. Now bit 0 in the plus basis will be the horizontally polarized photon, which we have this. Bit 1 in the cross basis will be the right diagonal polarized photon. Bit 1 in the plus basis will be the vertical photon. Bit 0 in the cross basis will be the left diagonal photon, and so on. So the choice of what photons to use depends upon both the bit sequence and the preparation bit. So the same one, if it's the plus basis gets encoded as the vertical photon. If the same one, if it's the cross basis, it is encoded as the right diagonal photon. Only Alice knows the photon sequence. Bob knows nothing. Bob doesn't know this bits. Bob doesn't know this preparation bits. Okay, and Bob receives these bits. Now what Bob will do? Bob makes his own random choice of detection basis. So Bob doesn't know what is Alice's preparation basis. So he just chooses his own basis randomly and independently values. No idea. So you can see this is Bob's detection basis. So sometimes it agrees with Alice, sometimes it doesn't. 50% on an average, it will agree with Alice, 50% no. But anyway, so that detection basis basically decides how you will place his filters. And then you have to follow the filters by another standard optical thing called a beam splitter. So which will send so let us say if you're taking the plus basis, the vertically polarized photon will go to this detector, the horizontally polarized photon will go to this detector. So I'll call this 1 and this 0. If it is if you have chosen the diagonal Polaroid filter, then the right diagonal will go to this detector, the left diagonal will go to the other detector. Okay, so this is how the measurement is done after the choice of basis. So and you can see the measurement outcomes of Bob. Again, he gets zeros and ones. Now see what is happening. So if Bob's detection basis agrees with Alice's preparation basis, he is going to decode the same value of the bit. So these locations where I put in numbers here, so these are, you can see where the basis agrees. So here, for example, this is plus, this is plus. Okay. Here, for example, this is plus and this is cross. So this is nonsense. Okay. So there are some points, there are some locations where Bob's measurement has agreed with Alice. So the bit values that Bob gets here, which I'm calling the shifted key, they will agree with what Alice said. Bob also gets bit values for the other locations, but they are junk. I'm not showing it here, but remember, Bob doesn't know what is Alice's preparation is. So he doesn't know which is the shifted key and which is the junk part at this point. So he gets a full sequence. He doesn't know what to use, what not. That will come later. But this is the first step. Now, the second step is Bob will only keep those positions where the preparation and measurement basis agree. Okay. How does Bob know that? So after the first step is done, Alice announces her preparation basis. So this is announced through a public channel. Even the eavesdropper can see it. The eavesdropper cannot tamper with it, but the eavesdropper can see exactly what is the preparation basis of Alice. Okay, so this is a tamper-proof public channel. So this can be done by classical cryptography. No issue about that. Okay. So after Alice announces the preparation basis, Bob does not declare his detection basis. Okay, that cannot be declared. But Bob knows internally what are the good locations, so he can pull out the shifted key from there. Okay, so about half the locations will be bad, half the locations will be good. So the shifted key length has already become around half. Okay. Okay. So how is this done? Eve can see Alice's preparation basis, but cannot alter it due to a classical cryptographic procedure called a digital signature. Okay. Now, but remember, Eve can try to tamper with these photons. That is allowed. She cannot tamper with the preparation basis because of the digital signature. But photons is a quantum thing. There is no signature for quantum stuff. So Eve can try to tamper with it. So how do Alice and Bob detect this possible tampering? Okay. So Alice reveals a small subset of her bit sequence, the actual bit sequence that she used. Remember, Alice does not know the location of the shifted key because Alice does not know Bob's detection basis. So she reveals a small subset. So some of those locations will be the junk positions. But again, about 25% locations she reveals will be the shifted position. So that gets revealed. So even Eve can see that. Okay, Eve can see that, Bob can see that. So Eve already knows about 25% of Alice's bits out here. Okay, really scary. Now, what will Bob see? Bob will check whether Alice's revealed subset agrees with Bob's outcomes there. Now, the point is that any attempt by Eve to gain information about the photons will amount to a quantum measurement, which will disturb the quantum state. And then in this agreement step, Bob will see a discrepancy. So Eve is tampering. Bob will see that in the revealed subset, there's discrepancy between what Alice has revealed and what he has measured. So if he sees this discrepancy, he'll just abort the protocol. Okay. If he doesn't see the discrepancy, then he knows for sure that Alice has not tampered with the photons out here. Okay. So note that Eve can see but not alter Alice's revealed bit sequence, again because of the signature, digital signature. So if everything is okay, then what happens is that on the remaining shifted key, so already I have lost quite a bit of the shifted key, Alice and Bob will apply another classical cryptographic procedure called a strong extractor. So they will extract a smaller number of bits from the unrevealed shifted key. And this smaller number turns out to be totally unknown to Eve and everybody else in the universe. And this forms the final secured secret. So note what we have achieved. So Alice and Bob have never met physically. There's an eavesdropper in the middle. Okay. But still, they can finally come up with a secure secret key, which is unknown to everybody, which can be used for later one-time pad, or they will detect some malicious activity. Okay. Yeah. So it turns out now you'll say that either Alice touches some photons and then Bob aborts, okay, or she doesn't touch anything. It looks really extreme, but actually the situation is better than that. So even if Eve is trying to gain information about Alice's transmitted photons, as long as she touches less than 10% of them, okay, the final secret key, which we had done at the very last step, this last step, the final secret key using the extractor, okay, that final secret key will still be totally secure for me. So this is classical cryptographic magic, you can say. Okay. So, but Eve has to touch less than 10%. So why is this? Because even after knowing Alice's preparation basis and the revealed bit sequence, Eve has no control over Bob's measurement outcomes on the unrevealed photons because of our quantum property. So what will Bob do? Bob will look at the amount of disagreement between Alice's reveal bits and his measurement outcomes. If the disagreement is more than 10%, he'll abort the key distribution protocol. If it is less than 10%, he'll just continue with the rest of the protocol, apply the strong extractor, and he is very sure that the final secret key will be unknown to you. Okay.
Is it always assumed that for the extractor is always coming from a secure source? What is the seed?
Okay. Yes. The seed is coming from secure source. So what happens is Alice tosses the random coins required to create the seed for the extractor and sends it through the same public tamper-proof channel. So Eve can see the key of the extractor. It's a short key. Okay, easy to create. Eve can see that, but she cannot tamper with it. Okay, I hope this answers the question. Okay, so Alice generates the seed of the extractor, sends it to the same tamper-proof channel, classical channel. So yes, yeah. So the question is, there should be a back communication from Bob to Alice, because after everything is done, Bob has to say what are the unrevealed shifted positions. Okay, because Alice and Bob will have to agree on the final security. Sure, he does that. Eve can see that, but that doesn't matter because the extractor has taken care of that. Yeah. Question? Very good question. So this is called, okay, so the question is, what if Eve acts like Bob and tries to figure out the secret key? So this is a very famous attack in cryptography. It's called man, in this case, woman in the middle attack. Nothing can be done about it. Okay, so we assume that Eve cannot act like Bob. Now, how do you do it? Normally, I mean, we'll assume that Alice and Bob are separated well in space, and then they have put shields around them. So Eve cannot physically be close to Bob, things like that. But there is no good protection against man in the middle attack. Okay, we're just assuming that some engineering things have been done to prevent us from man in the middle. Okay. I mean, you can try putting signatures and all that to get some extra security, but yes, this is always a vulnerability. Question. Yeah. 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 Okay. So the question was, if Eve is sitting in the middle and trying to measure something, measure the polarization or change the polarization or affect it in some way, and after that, Bob is trying also to measure the polarization. So yes, so there will be a double measurement. So this amounts to a disturbance, which will show up as a disagreement in the revealed subset. Okay, so that's what is called quantum magic. Okay, so measurement by Bob will not amount to a disagreement. Any action by Eve in the middle will amount to a disagreement when they are doing consistency check on the revealed set. Yeah, so 10% disagreement is okay. So 10% disagreement is good enough that the strong extractor here can distill the final secure key from there. So why 10%? I'll comment on that. I mean, those are difficult questions. Okay. Yeah. Okay. So so what have we learned? So the key was created without Alice and Bob ever physically meeting. The secret key can be used as a one-time pad for future communication. Yes. Question. No, okay, so the question was, how does Bob know which photons are diagonal, which are horizontal? How does Bob know which is plus or cross? So the answer is Bob does not know Alice's preparation basis. He doesn't know whether Alice has chosen plus or crosses. He randomly makes his own choice of pluses and crosses. So that's the detection basis. No, so if you have to do a detection, you have to make a choice of basis. So the choice is only a plus or cross. So Bob does it independently of Alice. So that's why I said in 50% of locations, Bob's choice will not agree with Alice's choice. So they are the blanks out here, which is the junk. Okay, Bob is anyway going to throw it away. So is the remaining 50% where the two choices of basis, the preparation basis and the detection basis agreed. So you see, they agreed here, they agreed here. So you can see wherever these numbers are that they agreed. And that is the shifted key, which will be used for later purposes. So already 50% of the original raw bit sequence is lost. So there are enough losses, but at the end, they will still get a reasonable amount of secret key. Okay. Yeah. Okay, so the question was, can Alice use different symbols or different quantum states other than vertical or diagonal? So actually, she can use any two bases. So she has to use two different bases. So she can use any two bases which are basically at 45 degrees with respect to each other. So they are called mutually unbiased. That's a technical term. So you can see that the plus and the cross are basically rotated by 45 degrees. So basically, any pair of bases which are rotated 45 degrees can be used. But I will say more about this in the next slide. Okay. So yeah, so there were questions like, I mean, this was very mysterious. I mean, if Eve does something in the middle, I'm claiming without proof that that will amount to a disturbance which will show up at Bob's end because there'll be disagreement. There'll be too much disagreement beyond 10%, so on. So all these are very difficult statements to prove. So actually, the complete mathematical proof of the above statement is highly non-trivial. And it was only provided in 1996 by Peter Shor, the fourth breakthrough laureate, 22 years after Bennett and Brassard proposed their protocol. So they just proposed the protocol at a small conference in Bangalore, based entirely on physics intuition. They had no mathematical way of modeling it. They had absolutely no proof, mathematical proof of security. It's only Peter Shor. Huh? Or 12 years, sorry. Okay. So 12 years, yeah. Sorry, about 12 years. In 1996, Peter Shor gives the first proof. It's been simplified a little bit since then, but there is no very simple proof of it. Okay. But if you go through that proof, you'll understand where the 10% is coming from. And now I'm coming to this gentleman's question about the plus basis and the cross basis. So it turns out there's a third basis. Okay. So let's see for the two. So there is the plus basis, there's a cross basis, there's a cross basis which is kind of like this in 3D. Okay, so that's actually, if you know polarization, this was the vertical and horizontal polarization. This was the left diagonal, right diagonal polarization. This one is the right circular and the left circular polarization of photons. So this third basis is also at 45 degrees to the other two bases. So that is a souped up BB84. It's called the 6-state BB84 protocol. What you've seen is the 4-state BB84 protocol because there are 4 types of photons. You can take the 6-state BB84 protocol. That actually improves the security guarantee from 10% to about 21 or 22%. Okay, but you do need bases which are at 45 degrees with respect to each other. Unfortunately, if you're working polarization, that's it. There is no fourth basis which is at 45 degrees to all of them. This you can mathematically prove. So this is about as far as BB84 can go. Okay, but in the original description, they didn't know all these things. They just used these. I mean, the most common basis in the lab. Question? Huh? Yeah. So that will drop. But overall, I mean, the disagreement tolerance will rise up from 10% to about 21%. So overall, you will win there. Yes. Good question. Yeah. So the question was, if there are 3 bases used, then the agreement between Bob's basis and Alice's basis will drop from 50% to 33%. Yes, that's true. So the size of the shifted key is smaller, but then the disagreement tolerance rises from 10 to 21%. So eventually you still win because of this. There's a question coming. Very good question. So actually, Bennett in 1992, he didn't use a basis. So, okay, a basis will not work. What you need is 2 different states of the photons, okay, 2 different polarizations which are not at 90 degrees. So you can take the vertical polarization and let's say the right diagonal polarization and come up with a 2-state protocol. So this is called the Bennett 1992 protocol. Okay, that also achieves secure quantum key distribution. The final tolerance and rate is below 10%, so that's why people maybe don't use it in practice. Okay, yeah. So the question was, what happens is instead of 2 bases, we use 1 basis. So the answer is, well, you cannot use a basis, but you can use 2 non-orthogonal polarization states like vertical and horizontal and the right diagonal, for example. That's the Bennett 1990 protocol. It turns out the security proof of that is even more difficult than that of the BB84 protocol, provided a few years after this. But yes, you can get quantum key distribution there.
Just a small request. Please hold your question. You can take your question
after the, yeah. In fact, I should bring in the TIFR angle. So there is a researcher, Professor Sushil Mojumdar at TIFR. So he's actually working on implementing the Bennett 92 protocol with just vertical and right diagonal polarization states of photons. So in TIFR Mumbai, he does it with an optical fiber in our basement. But the better experiment he is doing at the GMRT, the Giant Meter Radio Telescope, Pune, Narayangaon near Pune. So there they have about 1 kilometer line of sight between 2 hills or something, and they're working with that experiment. Huh? Okay. 500 meters, so not 1 kilometer. Achha. Distance 500. Okay, not one. Yeah. Yeah, so the distance is 500 meters, half. Huh?
5 kilometers.
Oh, 5 kilometers. Oh, they found 2 hills at 5 kilometers. Ah, wow. This I didn't know. Okay, 5 kilometers apart. Yeah. Yeah, good. Yeah, in the Alps, BB84 was implemented a long time back in Austria as 7 kilometers, but that was BB84. I'm not sure how much Bennett 92, B92 has been implemented. This might be the best one. Okay. Okay, so enough about quantum cryptography. Let's. So we have understood a little bit about the works of Bennett and Brassard, but let's go on to the other 2 laureates, Deutsch and Shor. So independent of Bennett and Brassard, and inspired by the thoughts of Feynman and Benioff, okay, David Deutsch from Oxford University in 1985 defined a quantum version of a mathematical model of computation called Turing machine. So, I mean, we have computers. I mean, even your mobile phone is a very powerful computer these days. There is a mathematical abstract model of computation which you use in theoretical computer science called Turing machine. So, inspired by considerations of Feynman and Benioff, David Deutsch decided to define a quantum analog of Turing machine, which he called the quantum Turing machine. So to understand the quantum Turing machine, we need to understand the basic unit of information storage in a standard classical computer. Okay, we know it's the bit. Then we'll see how to make the bit quantum. Okay, so the bit is the basic unit of information storage. It's short for binary digit. But from the physics point of view, it's a physical system that at any point of time is in exactly one of 2 well-defined distinct states. So conventionally, these states are called 0 and 1. Okay. But here's where the physics comes in. So if a bit is a physical system, deep down, it must obey the laws of quantum mechanics. This is actually what Feynman and Benioff said. Now, the question is, does this quantum reality deep down change the information processing properties too? So the question is, does it make the informational aspects of the bit, not the technological aspects? Technologically, we know there is quantum mechanics at the bottom of the transistor. But the way we use the transistor in our computer, the informational aspects of transistor are classical bits. But the question is, can the deep down quantum nature change the informational aspects of the bit and make it different from what we have been believing so far? So that's the question. So it's a fundamental question which was not asked before. Okay. So let's get more into it. So a standard example of a bit in a physical system is a transistor. Okay, so this is schematic of a transistor. So the technological aspects of a transistor require quantum mechanics to explain. But as far as the informational aspects are concerned, we can just model it as a switch like the one here. So at any point of time, the transistor is in exactly one of 2 well-defined distinct states. So I'll say it's either off when no current is flowing through it. So people who know transistor electronics will call it the cutoff state, or it is on, current is flowing through it. It's called the saturation state. Okay, so you can see the on and the off states out here in this schematic diagram. So we'll call them 0 and 1. So as far as the informational aspects are concerned, the transistor can either be on or off. That's it, 2 states. Whereas a quantum bit, called qubit for short, is a quantum physical system. So what is the property? If measured, it will give exactly one of two well-defined physical outcomes. One of two well-defined distinct outcomes. Let us call them 0 and 1. This symbol is called the ket. I'm just putting it here to emphasize that this is a quantum bit, okay, to distinguish. Okay, so this is kind of like the polarization state of the photon that we just saw. If we measure, we just see one of two possible states, but in reality, there are other polarization states, what I've told you. So that's a quantum bit. So in reality, there are other states also. But if you measure it, you'll only get one of two possible states. Okay. Let's see. Yeah. So a standard example of a qubit is the spin of an electron. So what is the spin of an electron? An electron possesses an intrinsic magnetic moment. Okay. So magnetic moment is like the polarity of a magnet, north pole, south pole of a magnet. So an electron behaves like a teeny tiny bar magnet with its own north pole and south pole. It's always there. Okay. So this is called the spin. It is as if the electron is like a tiny charged sphere spinning around an axis. So, I mean, this is just a cartoon model. In reality, the electron is a point particle, so you cannot think of it as actually physically spinning, but it nevertheless has its own internal magnetic moment, okay, magnetic polarity, and that's called spin because it's reminiscent of this behavior. Okay, and the spin has an axis. So this is, let's say, the north pole, this is the south pole. Here the spin is aligned in the opposite direction. This is the north pole, this is the south pole. Now, how do you measure the electron spin? Now, I claim the electron spin is a quantum property. So if you try to measure it, you have to, so polarization was measured by putting Polaroid filter. Spin I measure by applying an external magnetic field. So let us say I measure the spin by applying an external field in this vertical direction. Okay. Now, exactly one of two outcomes will occur. So either the magnetic moment is aligned parallel to the field, that means the north pole is up, south pole is down. So this is a parallel alignment, or it is measured to be anti-parallel to the field. That means the north pole is down, the south pole is up. Let's say the field is going from down to up. Okay, but on measuring, you get exactly one of these two outcomes, which we'll call spin up, spin down, and ket 0, ket 1. Yeah. Okay. So the question was, yeah. Yeah. So the question was, can spin only be measured in the vertical axis? How about horizontal? How about east-west? How about diagonal? So of course not. Spin can be measured along any axis. Okay. It's like putting a Polaroid filter with planar polarization along any axis. It's very similar to that. So spin can be measured even in the diagonal axis. But then what will happen is that you'll get two measurement outcomes. Either the spin is aligned parallel to the field, okay, or it is aligned anti-parallel to the field. So either the north pole is pointing up and right, or the north pole is pointing down and left. That's what you'll get. Okay. So always two outcomes. Okay. And you can see it's very similar to the photon polarization, which we measure by putting a Polaroid filter, let's say in the vertical direction. Exactly one of two outcomes result. So this is the analogy between electron spin and the photon polarization. So either the photon passes through the filter, in which case it is vertically polarized, or it gets reflected from the filter, in which case it is horizontally polarized, and we'll call them 0 and 1. So they're very analogous. So as far as the informational aspects are concerned, photon polarization and electron spin are one and the same. So let me repeat, as far as the informational aspects are concerned, don't stretch it and say that as far as all the physics are concerned, photon polarization is electron spin. That's not true. But today we are only looking at the informational aspects, and these two are exactly the same for us. So they are what we call quantum bits, two-level quantum systems. Okay. Okay. However, quantum mechanics tells us that these two outcomes are not the only possible states that a qubit can exist in. We have already seen the polarization can be along any plane. Okay, the spin can be aligned along any axis in 3D. Okay, so now it turns out that the set of all possible states is described mathematically as a combination. So the jargon uses superposition of the two outcomes. So that, remember, the measurement only gives two outcomes, which I'm calling ket 0 and ket 1. Mathematically, the set of all possible states is actually, there are infinitely many of them. It's a superposition which is written algebraically like this. Some linear combination of this. So right now it's just some algebra. So think of it as some amount of 0 and some amount of 1 at the same time. Okay, superposition, one on top of the other. What does this physically mean? So you can see the measurement outcomes can be ket 0, spin aligned up, or ket 1, spin aligned down. Okay, but a general spin, if not measured, can be along any axis in 3D. But this is mathematically modeled as a superposition of the up and the down out here. Okay, so a spin physically, it means a spin can point in any direction, and the plane of oscillation or the plane of polarization of the electric field of photon can be oriented anyhow in 3 dimensions. So this is the physics, this is the mathematics. And mathematically, you can see it's a linear combination of the two possible outcomes. So the coefficients which I'm calling A0 and A1, they're complex numbers whose absolute value squares will add up to 1. Okay. So we saw the algebra, we saw the physics. Let's see the geometry. Geometrically, the state of any qubit can be described by a point on the surface of a sphere in 3-dimensional space. It's like the spin being aligned in along any direction in 3D. So you can see like the spin is aligned along a particular direction in 3D. It's touching one particular point on the sphere. Okay, so that's the block sphere representation. So this is a geometric representation of a qubit. Okay. Now, the algebraic description of superposition allows us to think of states of 2 qubits. Now I'm moving from 1 qubit to 2 qubits. So if the 2 qubits, if I measure them, then there are 4 possible outcomes: 0, 0, 0, 1, 1, 0, 1, 1, like up, 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 down, down, up, or down, down. Okay. Now, the algebraic description says that we should be able to write algebraic quantities which look like this: a superposition or a combination of the 0, 0 and the 1, 1 states. Okay, and you can see the coefficient that I put in 1 upon square root 2, so that the square and add up to 1. So these kinds of states have very interesting mathematical properties. They are called entangled states. They were first discovered by Einstein, Podolsky, and Rosen in 1935, and they are called EPR states in deference to the 3 authors. And this was it's a seminal paper by EPR. Now, EPR did not like these states. They said that if you believe in superposition, if you believe in all these formulas of quantum mechanics, these states are mathematically allowed, so they should be there. But they did not like this because they thought that their existence implied that the physics is showing action at a distance. So we'll see what it means. Now, action at a distance is bad, especially bad for Einstein and relativity, because this violates a fundamental tenet of physics called causality. So we'll understand what this means. Okay. So this leads to what EPR called a paradox. Okay, the EPR paradox. So let us say an EPR state of 2 quantum bits is created on the Earth. Okay. Subsequently, 1 qubit remains on Earth and the other is taken to the moon. Let's say I prepare 2 electron spins in this EPR state, and then 1 electron is taken to the moon. So after it reaches the moon, next day at 9 AM IST sharp, the Earth and moon qubits are measured at their respective localities. Now the quantum theory will predict that the outcomes are perfectly correlated. So either both are measured to be 0 or both are measured to be 1. You can see it from here. Note that the 0, 0 and the 1, 1 outcomes individually have a probability of 50%. So 50% will get 0, 0, 50% will get 1, 1. So it's impossible to predict the outcomes in advance. It's not as if the movement of the electron from the Earth to the moon has changed the state to 0, 0. No, that has not happened. Because if you repeat this experiment with different space flights, on half the days you will see the outcome 0, 0, half the days you'll see the outcome 0, 1, 1. So the transport is not changing the state of the qubits. But somehow the measurement is creating a disturbance, which we know it's fine, but it's creating a correlated disturbance. So EPR did not like this. So they thought that somehow this would mean that the Earth and the moon qubits are signaling to each other faster than light. They're sort of telling each other what to do instantaneously. Okay, it's as if the Earth is deciding that, okay, you have disturbed me by measuring me, I will now collapse to 0, and immediately signals the moon qubit that you better go down to 0. So in particular, light itself takes 1.3 seconds to go from moon to the Earth. Okay, whereas the quantum theory is sort of saying that at 9 AM sharp, you do it, you will get correlated outcomes, which you can check later on. So this violates the cause and effect tenet of physics, which is called causality. So this is what is called action at distance. It seems that some signaling, some cause and effect thing is going on faster than light. So that's called action at a distance. Einstein hated it. He developed a theory of relativity. special and general in order to get around it. He did not like Newton's theory of gravitation because that was action at a distance. So he came up with general theory of relativity and gravitational waves, which you may have heard about recently. Okay, and now what is this? EPR is violating, quantum mechanics is violating causality. Okay, so EPR, actually the title of the paper was Quantum Theory is Incomplete. So they thought quantum theory is an incomplete theory of nature. So they felt that there will be better theory in future, which will only have local effects. It will not violate causality somehow. And then somehow it will address what they thought to be this paradox. Okay, they said that this description by superpositions is incomplete. There has to be deeper theory which will get around it. It will be local, no action at a distance, and it will somehow not violate causality. Okay. Now, after about 90 years of experiments, which have confirmed and deepened our understanding of quantum theory, so they have given us great confidence to answer EPR now. And that confidence has been bolstered by important theoretical work in quantum mechanics from the information perspective, what is called quantum information. So now we know that the EPR experiment cannot be used for signaling information instantaneously from the Earth to the moon. So it's true that the correlation is there. The correlated collapse occurs instantaneously. That is true. Still, you cannot actually signal information. So for that, you have to mathematically describe what you mean by signaling information. But it turns out that you cannot signal information by this experiment. So there is no violation of causality. So causality is moving from something local to something which is non-local and informational. So the only remaining question is whether nature is inherently classical and local, which is what EPR thought there will be deeper theory, or it is quantum mechanical and non-local in its microscopic description. Okay. So there's no causality is not a problem. The only problem is locality versus non-locality. So this was mathematically studied by Bell in 1964 in a deep way. And it was further mathematically defined by Clauser, Horn, Shimoni, and Holt in a seminal paper in 1989 called the CHSH paper. So they described an experiment called the CHSH game, whose success probability is at most 75% if nature is local, but it turns out to be 85% if nature is non-local and quantum mechanical. Okay, so they converted these philosophical questions of action at a distance or locality into a concrete experiment. They converted into a mathematical question and then into a physical experiment. They proposed an experiment. Okay. So the CHS game is very easy to describe. So again, there are two parties, Alice and Bob. They cannot communicate with each other. Let's say there's a wall between them, or they're spatially separated. Alice is on Earth, Bob is on the moon, something like that. Okay. Then there's a referee. So the referee, let's say, is sitting halfway between Earth and moon. So the referee can individually communicate to Alice faster than what Alice can communicate to Bob. Okay, the referee, let's say, sitting halfway between Earth and moon. The referee sends a bit X to Alice, sends a bit Y to Bob, and Alice has to reply with a bit A, Bob has to reply with a bit B. Okay, and Alice and Bob will win the game against the referee if this condition is true, if the AND of the bits X and Y is equal to the XOR of the bits A and B. So AND basically means that the AND will be 1 if and only if both X and Y are 1, and the XOR will be 1 if A is not equal to B, and the XOR will be 0 if A is not equal to B. So this is the condition, if you don't know the terminology. So there's a naive classical strategy. Okay, and Alice and Bob actually are very lazy and do nothing. They always send the bit 0. So Alice will always send A equal to 0. Bob will always send B equal to 0, irrespective of what X and Y are. They'll not even bother to. Now this works with 75% probability already, because I know that X and Y is 1 if and only if both X is 1 and Y is 1, which will only occur with 25% probability. Remaining 75% X and Y is 0, and A is 0, B is 0, they're equal, so the XOR is 0. Game solved. So it turns out that no local strategy that Alice and Bob can do better than this naive strategy. So this is the CHSH inequality for local strategies. But quantumly, however, it turns out that the following thing can be done. So Alice and Bob would have met one day before this game is played. Okay, they shared 1 qubit each of the EPR state, the famous EPR state, which we saw. This EPR state. So Alice shares 1 qubit, Bob shares another qubit, and now the qubits are at the Earth and the moon. Okay, and they have done this before the game starts. So note that when the EPR state was created, Alice does not know what X is going to come, Bob does not know what Y is going to come. Okay, so this is done prior. Then there's a clever strategy involving clever local measurements. So there'll be local measurements only at Alice's end and Bob's N. The measurement will depend upon Bob's measurement will depend on Y, and there will be some measurement on Bob's qubit of the EPR state. Alice's measurement will depend on X and will only act on Alice's qubit of the EPR state. And after the result of that measurement, they can do some classical computation and come up with the answers A and B, such that this equality is satisfied 85% of the time. Okay, quantum magic out here. So, but this is what I mean, CHSL showed that if you allow them to share EPR states, there's a quantum strategy, okay, which seems non-local and works with 85%. Okay. Now, this is an experiment with photons and everything, so you should be able to do it. So this was actually done by Alain Aspect in 1982, okay, in Paris. It's a path-breaking experiment. He used photon polarization as the qubit. He used photonic EPR states. He created two spatially separated Alice and Bob. Okay, so they were not separated as far as the Earth and the Moon, but they were separated well enough in the lab that by very precise timing, he can make out that there is no communication between them. Okay, and he obtained success probability greater than 75%. Equipment was not good those days, so he could not go up to 85%, but it was clearly more than 75%. So this was the first experimental confirmation that nature is non-local but causal. Okay. Subsequently, the experiment has been refined and performed many times. These days, the success probability is close to the quantum prediction of 85%. Okay. And important experimental advances were made with entangled photons. So Aspect worked with, remember, photonic EPR state. So you need entangled photons. So it's not easy to entangle photons because photons move very fast, okay, speed of light. So important experimental advances with entangled photons were made by Anton Zeilinger working at University of Vienna in the 1990s. So these advances play a crucial role in the modern experiments on the CHSH inequalities, as well as in experiments involving quantum key distribution and the BB84 protocol. Okay, a lot of experimental work in photonics. So for theoretical and experimental work on entangled photons and non-locality, so Alain Aspect, John Clauser at Berkeley, and Zeilinger at Vienna got the Nobel Prize for Physics in 2020. So, and you can see the connection to the breakthrough prize at BB84 out here already. So it's all part of the same picture. Questions? Okay. So let's get back to the next two laureates, Deutsch and Shor. Yes, question? They can send a message, but that will not help because they don't know what is X and Y. Before the game starts, they don't know what is X and Y. The X and Y are revealed by the referee only after the game starts. So they could do all that, but that's not going to help them. Okay, so the question was, can Alice send a message to Bob before the game starts? It changes nothing because X and Y are revealed only after the game starts. Okay, so let's come to what David Deutsch did. So Deutsch's model of a quantum computer. So he tried defining a quantum Turing machine. So a classical Turing machine is this toy kind of computer which has an infinite tape where you can write some symbols, zeros and ones. Then there's what is called the finite control of this, which is like the program you are running on a computer. So that's described by this graph, which is called a transition diagram. We'll not get into that, but it has just simple instructions like write a symbol on the tape, read a symbol, go move the tape head to the next location, right or left, or stop the computation. Okay. So what you write depends upon the symbol that is already here, that is being read by this finite control, and then depending upon what is the state of the finite control and the symbol read, you decide what is the action, what to write, which way to move the head. All this is encoded here in these arrows. Okay, so this is called the transition diagram. So in a quantum Turing machine, the state of the tape is a quantum superposition of the classical tapes. So again, there's an infinite tape, but this tape is a superposition not just of 0011, but now there are many zeros and ones, so huge bit strings. Okay, it's a superposition of all of them. So that's the state of the tape. The transition diagram is as before, but it respects the superposition. So the transition diagram acts on the superposition of tape states in the so-called natural fashion, or the people who know algebra, it acts in the linear fashion on that. Okay, so this was the model of David Deutsch. So it's something very abstract, doesn't look very good, but it was the first time somebody thought of converting a classical computer model into something quantum. Okay, Unfortunately, the quantum Turing machine is mathematically very uneasy to work with. So Deutsch, after this, also described another model of a quantum computer, which he called the quantum circuit. So this is a schematic of a quantum circuit. So you can see it has got wires, which will carry quantum bits now. Okay. So this is like the wires in my integrated circuit, which carry classical bits, classical information, but here they'll carry quantum bits. So this model mimics the classical Boolean circuit. So in the classical Boolean circuit, there are these operations on the wires, which are called the standard Boolean logic gates. Some of you may know them, the AND or NOT gates. So they are replaced by some basic quantum operations called quantum gates. So their names like quantum Fourier transform, which is the QFT here. Then there are measurement gates. You have to measure the quantum bits to get finally the zeros and the ones that you want. Okay. So this is like a natural mimic of the classical Boolean circuit model, but with quantum wires carrying quantum bits and quantum gates instead of classical gates. Now, quantum circuits are much easier to work with. And they're also nice because the gates correspond to actual physical operations that you can do in the laboratory with photon polarizations or the electron spins. So the model is useful theoretically, nice to work with, as well as experimentally, because you can do this in the lab. Okay. And in an important work, Andrew Yao showed in 1993 that the quantum circuit model of Deutsch and the earlier quantum Turing machine model, also by Deutsch, are mathematically equivalent. So a computation that you can do in the quantum Turing machine model, you can do in the circuit model and vice versa. They have the same computation power. So these days, nobody looks at quantum Turing machines. Everybody studies the quantum circuit model. Okay, so now so that is Deutsch. So he came up with a model for quantum computer. What did Shor do? So this is 1985. So in 1994, Shor comes into the picture. So Shor gave an algorithm for integer factoring. So factoring integer into its prime factors is believed to be a hard problem. No classical factoring algorithm is known that runs in time polynomial in the number of digits of the number to be factored. And the presumed hardness of factoring lies at the heart of many present-day crypto systems like the RSA crypto system, and they form the backbone of international banking, e-commerce, military communication, etc. Okay, you've probably heard of public key crypto systems and RSA. So an algorithm that factors an integer efficiently, that means in time polynomial in the number of digits, will cause a security catastrophe because this will break RSA and all the other crypto systems that are practically used. So you can see, I mean, the RSA company puts out challenges. So this is in 1991, they put out the RSA 100 challenge, factor this 100-digit number. It took quite some effort, but this is the factorization. So you can see, I mean, how difficult it looks. Okay. So there is no efficient classical algorithm known to this date. But in 1994, Shor gave a quantum circuit algorithm that factors an integer in time cubic in the number of its digits. So 100-digit number will take 100 cube time. Looks bad, but the classical algorithm would have taken 2 to the power 100 time, which is far, far worse. Okay. So this efficient quantum algorithm for integer factoring, you can see the circuit model here. So this sends shockwaves through the crypto community. Since then, quantum computation and information have been taken very seriously. Before that, I mean, Deutsch was working more or less on his own. Nobody really took him so seriously. But after Shor, immense theoretical and experimental effort has gone into designing more and better quantum algorithms, as well as building bigger and better experimental prototypes of a quantum computer. Okay, so now the pertinent question. So if you've seen the publicity flyer, so these questions are asked. So I mean, does this really deserve a breakthrough prize? Okay, so let's look at the pertinent question. So what is quantum information science? So studying the information properties of quantum systems, that is qubits, is quantum information science. So this can range for quantum algorithms for important tasks, so that outperform the best classical algorithms known. This can range for to quantum cryptography, so you can do cryptographic tasks that are impossible or difficult classically, as we saw. This can lead to more efficient communication of information through, let's say, optical fibers, communication channels that is possible classically. This can lead to better explanations of complex physical phenomena. People are trying to understand photosynthesis using quantum information science. Okay, things like that. People try to understand DNA pairing using quantum information science. Okay, then finally a deeper insight into how nature works at its most fundamental level also. So these all these fall under the ambit of quantum information science. So notable algorithmic advances. So a lot of water has flown down the rivers. So they include the quantum search algorithm of Love Grover. So he's from Bell Labs. Then there's a quantum algorithm, efficient, really fast quantum algorithm for solving linear equations, very basic algorithm by Harrow, Hasidim, and Lloyd. Then considerable scope exists for fast quantum algorithms for quantum chemistry, which may lead to intelligent drug design. Then fast quantum algorithms for machine learning, data science. So this is the reason why big companies like IBM and Google are heavily investing into it. Okay. Then besides BB84, notable cryptographic advances include an algorithm for information locking, quantum algorithm for information locking. Okay, together with Umar Fauzi and Patrick Hayden. Then quantum protocols can outperform classical coding protocols for communication over optical fibers in the low power regime. So when the optical fibers are the backbone of the undersea internet communication and over long distances the power goes very low. So it can be so low that even one photon gets transmitted at one point of time. In this low power regime, if you use quantum coding techniques, you can outperform the classical coding techniques used. Okay. So all that is quantum information science, but why haven't we heard more about it? So the answer is that is because it's still quite new and fresh. So whiffs of quantum information can be traced back to the works of von Neumann in the 1930s, who defined a quantum analog of entropy motivated by information and thermodynamics. Then there is Belavkin in the 1960s from the Soviet Union. So the West did not know about the fundamental work that he did. Then Holevo and Hellstrom in the 1970s, again in the Soviet Union. The West did not know about what they were thinking. They were really ahead of their time. And then finally, the West starts getting in. So Feynman, Benioff, and Manin start thinking about it in the 1980s. But the information theoretic lens, so I would like to call it a lens. It's a different way of even looking at questions in quantum mechanics. So this information theoretic lens took off in a big way only after Shor's discovery. Okay. And even then, for a long time, people thought that quantum computers will never be practical. But then, things move fast. So there was seminal work by Peter Shor. We already saw security of the BB84 protocol. Then Shor, Steen, Snell, Laflamme, Gottesman, and Dorit Arnott, they did very important work on quantum error correcting codes. Initially, people thought that there will be so much quantum noise that quantum computers will never be practical. But they said, no, we can counter quantum noise by quantum error correcting codes. We can build fault tolerant quantum computers, which can tolerate a low rate of faults that are occurring in your computer. Okay. So this addressed the theoretical misgivings. Okay. It seemed after their fundamental work that the only obstacles were technological, not fundamental. So there is quantum noise, but we have mathematical tools, error correction, fault tolerance, to mitigate it, provided the noise rate is low. That becomes technology. So how low? The theoretical numbers look like something like 0.1%. The numerical simulations look something like 3% or something. And currently people are maybe at around 10 to 20%. So that's why Google, IBM are trying to push to come to a low noise threshold. So even then people thought that the technological obstacles are almost insurmountable, but then the recent waves are by IBM, Google, and some other companies. So they have created immense excitement. Both of them had made prototypes of quantum computers containing around 70 qubits. They've shown that they can run some non-trivial algorithms, not Shor's algorithm, that is far too non-trivial, but some other algorithms, somewhat non-trivial, let's say. So these quantum computers still have very high noise rate, far above 3% or the noise tolerance threshold, but they're slowly going down. Still, the obstacles are very difficult, but at least they're trying. Okay. So the next part in question, is there even any breakthrough in it? Fine, this is good. So from a theoretical computer science aspect, the answer is a resounding yes. Okay. Now, let's look at experimental physics. So the experimental efforts to make quantum computers are expected to have highly beneficial side effects in designing better quantum control, quantum sensors, quantum metrology, where you are measuring physical variables, like say temperature, okay, distance, etc., but using quantum sensors, so quantum metrology. So this should have immense practical benefits. So this will be the spin-offs or side effects of quantum computers. So who knows, several breakthroughs may arise in unforeseen areas. From a theoretical physics aspect, quantum information science is giving new insights into quantum thermodynamics, quantum properties of novel materials. So there are, there's whole science called quantum materials. So they have all kinds of semiconductors, insulators, superconductors. Okay, so insights into their functioning are coming from quantum information science. At a more fundamental level, it may lead to very deep breakthroughs in understanding nature. So more on that in the next slide. So the amount of interest in this breakthrough can be gauged from the fact that US has announced a $1 billion quantum initiative. I mean, they already had a lot of investment, both public and private. On top of that is $1 billion. China, of course, overdoes the US by a factor of 10. Okay, they are doing quantum key distribution between satellites in space, between one end of China to the other via satellites, so on and so forth. Even our own finance minister announced 8,000 crores, so $1 billion. But then COVID came, so the money is still stuck. Okay, so what is fundamental about it? So the 2 points. So if a practical quantum computer is eventually built, so we would have verified that the basic tenets of quantum mechanics work all the way from microscopic level of individual spins to macroscopic level of a big quantum computer, like maybe as big as this room. So this would be an unprecedented stress test of a physical theory to a level of accuracy which has never been achieved before, all the way from microscopic to macroscopic to tremendous accuracy. Okay, if we fail, then this would mean that some basic tenet of quantum mechanics does not scale up. It's only an approximation. So either way, we would have learned something fundamental about nature. Okay. From a different perspective, quantum information science has injected new life into old, deep, and difficult questions about black holes, or more generally in the regime where quantum mechanics and general relativity come together. So fundamental work by Stephen Hawking, Bekenstein, and others in the 1970s about black hole entropy and radiation showed a very real possibility of information being lost from the universe due to a black hole. So this is called the black hole information paradox. And this goes against one of the basic tenets of quantum mechanics. Okay, so this was very unsatisfactory. So work by Don Page in the 1990s, followed by, so this is where QoS comes in, followed by spectacular application of quantum information science. In fact, followed by the application of quantum error correcting codes. Okay, so quantum error correcting codes were applied to black holes by Patrick Hayden at Stanford and John Preskill at Caltech in 2007. They showed how information can eventually leak out of a black hole by the Hawking radiation. So they have confirmed what Page suspected, but with far more, let's say, mathematical evidence. Of course, I mean, we cannot go near a black hole and really do the experiment, but it's very theoretical. But this is a very active area of research in fundamental physics stuff. Okay, so I would like to say that they indeed deserve the prize. So this is back to the poster again. So you can see still from the video. So Bennett and Brassard quantum cryptography, you can see the BB84 protocol, you can see the horizontally polarized photon, the diagonally polarized photon, the vertically polarized photon. They have not shown the other diagonally polarized, maybe because the picture was getting cluttered, but that's there in the protocol. Okay. Now, David Deutsch and Peter Shor came up with quantum bit, quantum computer, factoring integers efficiently, which will break RSA and present-day crypto. So this is how an experimental quantum computer from IBM looks like, the innards of the quantum computer. Okay, and this is the block sphere representation of a quantum bit, which we saw. Okay, so both these were there in the slides. This is how the actual IBM Q system 1 looks. It's a big thing. It's about as big as, I mean, from the floor to the ceiling and about this big. Okay, and this is actually enclosed in a huge glass case out there. I mean, you can get an idea. It's a huge lab. Okay, so this is how the quantum computer looks. So you see this big cylinder. The inside of it is this. Actually, the chip where the qubits are is at the very bottom. It's a very small thing. The rest of it is all wiring and cooling. This thing runs at 10 millikelvin. Okay, so you need fantastic cooling for that. Okay, so this is a standard computer chip in the 1990s. Okay, now we have better ones in our mobile phone. This is what, if you zoom into the chip with a scanning electron micrograph, you can see the transistors. So you can see, so these are the gold wires. So these are the wires where the bits will flow through. This junction is a transistor, which is about 1 micron big for 1990. Okay, and now the transistor is replaced by qubit, which is encoded on the same silicon chip using a Josephson junction. So these are various metallic wires. These are the junctions. you can see here, out here. Okay. Only difference is that this can work at room temperature or even 100 degrees Celsius. This needs to work at 10 millikelvin. Okay. So now we will conclude by seeing the same video again. Okay, but with annotations where we are explaining the various pictures. Okay, so now hopefully the fancy pictures will start making sense. So I think we'll have to stop the Bluetooth and yeah.
How do you transmit the sound out? It's enabled, huh? Yeah, so let's. Okay, so apologies in advance. I edited it using Filmora, the free version, so they put the watermark.
We live in a world of information, but physics tells us that deep down, the world is quantum mechanical. This year, the Breakthrough Prize recognizes 4 pioneers of quantum information. Charles Bennett and Gilles Brassard initiated quantum cryptography. And played a central role in the discovery of quantum teleportation.
So this is a simulation, but
David Deutsch defined the
huh? Yes. Yes. Okay.
We live in a world of information, but physics tells us that deep down, we live in a world of information.
So just wanted to remark that the first linear implementation and diffusion analysis that we different ones were so Brassard remarked that the protocol is simply only instantly.
David Deutsch defined the quantum Turing machine. And laid the foundations of quantum computation. And Peter Shor invented an algorithm that could factor large numbers exponentially faster than any non-quantum rival. With these and other advances, they paved the way for quantum computers and provided clues to questions. Physics for foundational work in the field of quantum information. They win the Breakthrough Prize in Fundamental Physics.
An exciting talk, and I think everybody is excited about the future. There are lots of opportunities opening up again. So before we open this talk next year.
Session.
So the next session, the 2 weeks from now, actually we'll be celebrating Founders Day at TIFR. So the next session will be online only, will be about another breakthrough prize. And 3 weeks from now, that is 6th of November, we'll have a session at Prithvi Theatre, and we'll talk about how artificial intelligence is helping understanding proteins. So that will be 3 weeks from now, 6th of November at Prithvi. So with this, I'll stopping the online thing and so we can ask